Hi, this video is on bond polarity and electronegativity. I'm following Brown, LeMay, Burston, and Murphy's chemistry textbook, Chemistry, the Central Science, but any chemistry textbook eventually is going to get to this subject. It's in a chapter. Chapter 8 is on bonding, various kinds of bonding. And up to this point in the chapter, we've talked about ionic bonds and we've talked about covalent bonds. And what we're going to find out in this section is that it's not just an either or, that there are these elements in between kind of the non-polar, well, let me just tell you, bond polarities. There are these non-polar covalent bonds. So like oxygen 2, chlorine 2, hydrogen 2, when you have the same molecule bound together in a covalent kind of way, covalent means they share the electrons, you have no polarity whatsoever. That is, there is no, the one chlorine isn't any more negative than the other chlorine. They share they're perfectly neutral in their sharing of the electrons. The electrons are shared equally between the two atoms in Cl2. That's called a non-polar covalent bond because there is no charge differentiation between the two atoms. But what we're finding in this section of the chapter is that you have the ionic bond on the other end of the spectrum where they just give up their electron altogether. And so there's a big charge differentiation in an ionic bond, like in lithium chloride. The lithium is very positive and the chlorine is very negative. The electron is very much more attracted to the chlorine. That's the ionic bond. But there's this middle level, like hydrogen chloride, where the hydrogen is a little bit more positive and the chlorine side is a little bit more negative. It's still a covalent bond. That is, the HCl is sharing the electrons more than trading them. Ionic bonds trade them. Covalent bonds share them. And so the HCl still is sharing the electrons, but within that bond, the bonding electrons are a little bit more attracted to the chlorine than they are to the hydrogen. So you get a little bit of polarity. Not as much as an ionic bond, but you get a little bit of polarity. So you have the nonpolar covalent bond where there's equal, no charge differentiation between the atoms at all. You have the polar covalent bond where there's a little bit more negativity on the one side than the other. And there's some lovely diagrams in my textbook that show a colored diagram of how the negativity is a little bit more on the one side than the other. And then, of course, on the other end of the spectrum, you have ionic bonds where the sodium basically says, here, take the electron, I don't want it. And so the chlorine pretty much takes the electron. And so you have a big charge differentiation between the sodium and the chlorine, with the sodium being +1 and the chlorine being -1, more or less. So so we're getting a little bit more complicated in this section. We've done ionic bonds, we've done covalent bonds. Now we're finding there's this middle ground, the polar covalent bond, as it were, that has a little bit of charge differentiation. Okay, let's talk about electronegativity. We've already talked about electronegativity by this point in any chemistry course, but electronegativity basically is the ability of an atom in a molecule to attract electrons to itself. And this is a total picture both of electronegativity has to do with the ability to keep the electrons it has and to attract other electrons that it doesn't have. Electronegativity is the total picture of the ability of an atom in a molecule to attract electrons to itself. So this relates to what's called the ionization energy. That's how strongly a gaseous version of an atom wants to hold on to its electrons. So on the far left side of the periodic table, the alkali metals, column 1, group 1, these atoms have a very low ionization energy. That is, they're like, here, take my electron. I don't want it. Take it. Lithium, sodium, take potassium, take my electron. Get rid of, these have a very low ionization energy, and they have a very low electronegativity. On the other end of the periodic table, on the far right, you have the halogens, for example. The halogens have very high ionization energies. They're not giving up their electrons. Do your worst. I'm not getting rid of my electron. And so the halogens in group 7 on the far right side of the periodic table have a very high electronegativity. And they also have a very high, the halogens have a very high electron affinity. That is, they not only hold on to their electrons, but they want to grab electrons from other unsuspecting atoms like sodium. And so this is there's a scale basically. Linus Pauling, a famous physicist of the 20th century, created a scale that went from 0.7 to 4.0. And basically this is the electronegativity scale. Cesium has a very low electronegativity because it has a very low ionization energy and a very low electron affinity. That is cesium on the far bottom over here. Remember, electronegativity goes from the bottom left to the top right of the periodic table, from low to high. And so cesium has a the lowest of all ionization energies. It'll give, you don't have to force it at all to get its electron. What gate key? Oh, you mean this gate key. So cesium's glad to give away its electron, whereas fluorine gets a perfect 4.0, 100%. Fluorine aced the exam. On the Linus Pauling scale of electronegativities, fluorine is 4.0 with the highest electronegativity. It's not given up any of its electrons, and it's glad to take anybody's more than anybody else. It feeds on electrons. Okay, so this is a chart from Brown, LeMay, Burston, and Murphy's Chemistry of the Central Science. And here, this basically reflects the Pauling scale of electronegativity. Over here you can see in blue, these have very low electronegativities, very low ionization energies, very low electron affinity. These are atoms that are glad, more than happy, to give you their electrons. And then on the other, so that's blue. Like, remember, cesium's 0.7. On the other end of the scale are these with very high electronegativity, 3 to 4 on the Pauling scale. They would love, give me your electrons. We would love to have them. And then you have these others that are in between. So these transition metals here and the semiconductors, silicon, germanium, these middle ones, they're a little bit more electronegative than these over here, but they're still not nearly as much as fluorine. And then you have yellow. The yellow ones are a little bit more electronegative than the green ones. And then, of course, as we said, the red ones here. So you can see, as we said, from the bottom left to the top right, electronegativity increases from 0.7 to 4.0. Okay, the difference in an electronegativity, that is, if you take the electronegativity of one atom and you subtract the electronegativity of the other atom, the difference tells you basically the polarity of the molecule, okay? And it tells you the type of bond. So if there's no difference between the electronegativity, so let's take F2, I meant fluorine 2, I think, FL2, fluorine 2. Take FL2. There is no, fluorine is F, isn't it? I'm sorry, I'm spacing out. It's F. Scratch that. F2, fluorine 2. So there's no difference in electronegativity between the one F and the other F because it's the same atom. And so there's a zero difference. There's a zero difference between the electronegativity of the one fluorine and the other fluorine. So this is going to be a nonpolar covalent bond. There's going to be no charge differentiation between the two fluorines in that molecule. Then there's the middle ground, this polar covalent ground, where it's in the Pauling 1 to 2 range, a middle level difference between one atom and the other item. So like a hydrogen fluoride, hydrogen fluoride, or hydrogen chloride, there's going to be a middle range difference. Now, of course, if it has a great difference, say from 2 to 3 on the Pauling scale, then it's going to be an ionic bond. So you see that the difference in electronegativity between two atoms that are bonding together is going to give you some indication. Now, it's not a foolproof thing. There are exceptions, but it's going to give you a general indication of what kind of bonding is probably going on. Okay, so the last thing we want to talk about, or second to last thing we want to talk about in this video, are what are called dipole moments. So in polar covalent bonds, there's some polarity between the atoms of the molecule. So hydrogen fluoride I have here. What is that polarity going to, how are we going to diagram that? Well, we can do it, we can show the dipole moment with a delta, that's the Greek delta plus, or delta minus. This is a little delta, by the way, for those of you who've had calculus and you're wondering, I thought a delta was a triangle. That's a capital delta. This is a little lowercase delta in Greek. So delta plus, delta minus, that tells us that the hydrogen is a little bit more positive in this, even though it's a covalent bond, and the fluorine is a little bit more negative. Or another way to do it is this arrow with the plus at the end. That tells you the H is a little bit more plus, and the electron's going to go more toward the bond. The electrons are going to go a little bit more toward the fluorine in the shared relationship. Okay, so how do we measure the bipole moment? By the way, let me show you the answer because it pops up right there. So you can see that in hydrogen chloride, this is really not a big difference. It's not +1 plus, -1. It's plus 0.178 and minus 0.178. So you can see that when we're talking about polar covalent bonds, we're not talking about the kind of charge differentiation that you get with an ionic bond. But how do we measure it? So the formula is mu, that's the Greek letter mu equals QR, where mu is the dipole moment, Q is the charge, and R is the difference, the distance between the center of the radius, the center of the nuclei, basically the distance between the two molecules. So the dipole moment, like this 0.178, is going to be the charge times the distance between the two atoms that are bonding together. Okay, now here's the problem. The problem is that the numbers at the bottom, 0.178, are called debye unit, based on the debye unit. What's the debye unit? Well, I'll get there in a second. But it's not, the problem is the debye unit isn't what we normally measure these things in. So charge is usually measured as a function of E, that is the charge of an electron. The charge of an electron is 1.6 times 10 to the minus 19 coulombs is a measure of charge. And so we don't have that in debyes. How do we get to it? Stay tuned. The distance, here's another problem. The distance is often measured in angstroms, which is an A with a little circle on top of it. And again, we're not yet to debyes. An angstrom is 1 times 10 to the minus 10 of a meter. So it's a very, very small unit. What about this debye thing you're talking about? Well, dipole moments are measured in debyes. And 1 debye is 3.34 times 10 to the minus 30 coulomb meters. So you're going to have to use a little bit of the factor label method to get this into the right, and he gives some examples in the textbook, because probably the charge is going to be measured in multiples of electron charge, and the distance is probably going to be measured in angstroms. And so you're going to have units given to you that aren't anywhere close to the unit you need to come up with this chart at the bottom. But this is basic, kind of working with units that you, by this point in your career, have done quite a bit of. I won't give you an example, but basically you're going to have to do a little bit of multiplication and division to get it into debyes. Okay, finally, I'll end this video with the difference between ionic versus covalent substances. How do they end up looking? So ionic substances actually are the smaller percentage of substances. Most substances are covalent in some way or another. Ionic substances tend to be brittle. They tend to be high melting, sometimes in the thousands, and they tend to have extended lattice cubic kind of structures, and they tend to again be electrolytic. You can run a charge through them. By contrast, substances that are based on covalent bonds, they tend to be stronger. That is, they hold together better. They tend to melt at lower melting temperatures, and they have other geometric structures. And stay tuned to the fun of the next chapter, and we go into all that tetrahedral stuff. And then, of course, covalent bonds tend to be non-electrolytic. Well, this is a lot of stuff. You may need to watch it more than once, but what we were doing in this video is we're trying to show what polar covalent bonds are like, and how that there's a spectrum of polarity between the two atoms in a bond, depending on these sorts of matters. So enjoy.